Hi, I'm Paul Battaglia, and this is section 4.5, Graphs of Sine and Cosine Functions. In section 4.5, students will be working with the general form of sine and cosine functions, and these involve constants. We're calling them A, B, C, and D. I think the best way to talk about this today is to actually talk about maybe an activity we can do with our classes, and then at the same time break down the meaning of each of these constants and how we would go about showing these to our students. So I have Gabe and Brittany with me today. And Gabe, I know you're going to start us off a little bit talking about an activity you do with your class.
So when it comes to this section, I like to just dive right in.
Okay.
And I really want to lay the foundation right away.
Okay.
So I want students to see the graphs of y equals sine of x and y equals cosine of x.
Okay.
And the way I have them do this is we go through some sort of guided activity, or I could even turn them loose and let them work through this.
Okay.
But what it is, more or less, is let's just take y equals sine of x, for instance.
Okay.
So I have them get out their unit circles. And I just say, okay, well, let's let the x-axis, or the horizontal axis, represent the angles on the unit circle.
Okay.
And the y-axis, well, it's going to represent the y points on our unit circle.
Okay.
So what we do is we go ahead and we'll start at an angle of 0.
Right.
And we know that sine of 0 is 0. That gives
Okay.
us our first point at 0, 0. And we'll move through the unit circle. So we'll come up to pi over 6. And we know that sine of pi over
Okay.
6, or the y value at pi over 6, is 1/2.
Okay.
And we'll go ahead, we'll plot all these
Point
points.
by point, okay.
And we'll get the general shape of what the graph looks like. And then what I'll have the students do once we make it all the way through 2 pi is connect all these points with a nice smooth curve. But then we have a little discussion about the domain of sine.
Okay.
This is something we've already talked about a couple times
Sure.
before. And we know that we don't just stop at 2 pi. We'll continue on. So
Right.
what this shows graphically is that, well, we can almost take the graph that we just found, pick it up, and place it
Move it
right
back.
at 2 pi. And we don't start at 0. We can start thinking about, well, what if we started at 0 and went down 45 degrees or went down
Okay,
90
right,
degrees? So we're taking our whole graph and we're shifting it off towards negative infinity also.
Okay.
So now they have the graph of y equals sine of x. I go through something similar, probably a little bit faster for y equals cosine of x.
Okay.
But that sets them up with, okay, this is the graph of sine, this is the graph of cosine, and then throughout the lesson, I'll probably reference a graphing utility, such as our calculators or Desmos,
Perfect.
to have them
Okay.
actually see what changing A, B, C, and D does to the
And
graph.
then they can play with it on their own, and then they're getting the idea of, and it actually helps you out too, because then you can ask them more questions instead of telling them more information.
Because I could stand up there and talk about phase shift and
Sure,
amplitude
right.
sort of all day long, but unless they actually see what changing those numbers do, they're not going to get much of a grasp
Okay.
of what it's doing
Right.
to the graph.
And it might be helpful before, or maybe as you're doing this, to actually list out the constants, A, B, C, and D, and say, okay, A stands for this, or if they do that activity, they can come back and say, what happened to the graph? Okay, when you changed A, so I noticed it kind of stretched a little bit. So all right, well, we call that a change in amplitude. And B refers to the frequency, and C refers to a phase shift, a horizontal translation, and D, a vertical translation. If you've kind of listed those out for students, now you can really dive into each one. I think that's what we should do. So, Brittany, how do you start off with them, with let's say A or B?
All right, I like to start out with A
Okay.
for amplitude. And I like to go back and reference the unit circle as Gabe was doing.
Okay.
And say, well, we saw that X and Y are range between 1 and -1.
Right.
And so now I say, well, now we're not looking at the unit circle. So now it can range from -A to A.
Okay.
Yeah.
So it really can stretch negative infinity to infinity.
Yeah, so we're talking about these transformations of graphs.
Yeah,
Right.
So that's something that
exactly.
I like to point out with, well, after I go through my graphing activity,
Right.
I say, hey, we're bouncing between -1 and 1. Well, if we take this whole function and we multiply it by 7,
Right.
now the lowest number we get is -7, and the highest
Right,
value we get
right.
is +7.
And I think this is great because now they've seen this already on their own, and now they're kind of equating it to prior libraries of functions and things like that, and they're seeing that all of those rules seem to still be in play for these trig graphs as well. And then how do you address the idea of period when it relates to the constant b, right? Because I see some students, they see b and they say, oh, that must be the period.
Yeah.
Yeah. So just kind of, I repeat myself a lot,
Right.
saying B is not for the period.
Right, the period's 2 pi divided by b.
Right, that's
Yeah.
it. Seeing that if
Exactly.
they see a constant, let's say of 3 for b, right? Seeing 3 cycles and having them say, well, okay, so the period being the length of one cycle, it wouldn't be 2 pi now. It'd have to be shortened up. you know.
And that's something that using something like Desmos to just represent what changing that b value does to your graph. So if you're making b larger, you're actually making the period smaller.
There you go.
So you want to think, well, what if I'm looking at something extreme, like y equals sine of 100x?
Right.
That period should be really small.
Right.
So your period shouldn't be 100. It's and then taking it back to the idea of the transformations of graphs. That's a horizontal shrink, not a stretch.
Yeah, perfect.
Yep, exactly.
Let's go to the constant c, phase shifts. What do you like to point out there?
Okay, so the phase shift doesn't just come from the constant c. It's also ties into the idea of it's c divided by b.
Right.
And it does kind of tie back into the idea of it being a horizontal shift.
Right.
So something else that I think students might get confused about, as always, is that when we're talking about this general form, it's a sine of bx minus c plus d, or a cosine of bx minus c. So here, this phase shift, we want it to be in that form minus c, and if it's, let's say, 3x minus 2, well, that phase shift is going to be 2/3 units to the right.
Right, and they're always thinking the opposite direction.
Yeah, and then they have to rewrite it if it's a plus sign. I know it's easy to think, oh, plus sign, we're moving to the right. Plus sign, we're moving up. But that's not always the case, especially when we're talking about these horizontal shifts or phase shifts.
Right, and depending on how intricate you'd like to get, keep in mind the idea that there are certain situations where you may actually have to factor that b value out before you truly see the actual phase shift. So that's something to point out to students as well. So I guess I'll take D. And so the constant d we've mentioned represents some type of a vertical translation. I've actually found myself using the term midline at some point with students just to get them to understand that that value will actually be, sometimes even when we graph it, we'll draw this dotted line through the middle of that cycle, so to speak. So they can see the difference in amplitude from that middle up and down as well. I found that to be pretty helpful.
That's something that I've seen students have misconceptions about also. So when you take that graph from the x-axis and you move it up or move it down, they tend to say, oh, well, the amplitude just goes from the lowest y value up to the highest y value, and it's actually half that number.
Exactly, right. I think if you're looking for a good way to kind of bring this all together and finish up, consider going online perhaps and finding a graph of maybe of your favorite city where you're looking at the sunrise in that city or the sunset or perhaps the hours of daylight in a given day. And what you'll actually find is, while not perfectly correlated to a sine or cosine function, it's highly periodic. And so you might be surprised to see that the graphs that you see for perhaps a 24-hour period actually mimic a sine or cosine graph pretty well. So pretty interesting stuff. I hope these tips have been helpful for you, that you find much success in section 4.5.